All right, so today I'm going to be talking about the stuff that we've been working on lately in my lab that's really focused on providing programming language technology, or say bringing programming language technology to support the sciences. So I want to start with a little story. These are two famous Harvard economists. They're Carmen Reinhart and Ken Rogoff. How many of you know this story? Oh, very few. All right, great. Reinhart and Rogoff published this working paper that was very influential. It's called Growth in a Time of Debt. And the conclusion of their paper, Growth in a Time of Debt, which involved an enormous study. They studied, I think, 20 countries and their GDP and their debt over the course of more than 100 years, some of the records going back to 1790. Okay? And they concluded that it appears that once you cross this 90% debt threshold, that is to say, debt over GDP ratio, then it triggers some sort of stagnation where economies kind of enter this death spiral, right? And then economic growth drops dramatically. So this proved to be a very influential document. It formed the basis of the Paul Ryan budget, which cited it heavily. It was discussed in congressional testimony. It was discussed by all sorts of pundits. It was also used, especially to great effect, to kind of have a lot of fun in Europe. They had lots of fireworks and excitement. Fires were set in buildings. This is a result of these austerity budgets that were put in place across Southern Europe, especially in Greece, and these triggered riots, right? So this was, boy, you better hope that this is correct, right? So the recipe essentially was, look, you need to cut debt. If you don't cut debt, which means that you need to cut spending, right, then your economy is going to go into a death spiral. So the conclusion to be drawn would be, well, we need austerity. So of course, I saw this study, and the first thing I thought of, and the first thing, this is the question I'm sure that's on all of your minds right now, what programming language did they use, right? Right, so I have a lot of experience in C++. I figured let's see what that C++ program looked like. This is maybe an oversimplification, but in any event, it turns out no, they did not use C++. Although it's a reasonable guess. There's about 3.5 million users of C++, so that's not so bad. So then, what other languages are there? So I figured, all right, potentially Java. Right? That's Java. Right. So it turns out, no, that it's not Java either, even though, again, good guess, better guess than C++. I'm sure you all, unfortunately, are aware which language it really was. It was Excel. All right? And yes, Excel is a programming language. It's a very peculiar programming language, but it's also an incredibly popular programming language. There are 500 million estimated users of just Excel, right? Not any other spreadsheet. And just to put this in perspective, that is 7% of the population of the world, right? So this definitely exceeds the reach of any of our conventional programming languages. So here is a glimpse of the Reinhart-Rogoff spreadsheet. I had to send them a few mails to pry it loose from them. And the spreadsheet, like I mentioned, it's ginormous. It's really hard to sort of see what's going on in it, but it turned out it had a lot of problems. And so this is a column by Paul Krugman, and he asks this question: did an Excel coding error destroy the economies of the Western world? And the answer is no. Many errors destroyed the economies of the Western world. So some colleagues of mine actually analyzed this spreadsheet. It took them months. These are some economists at UMass, by coincidence. And it turned out that the results were actually completely wrong. And just to give you a glimpse of what that means, the blue bars here are the reported Reinhart-Rogoff results for economic growth given certain debt GDP ratios. And the red ones are the corrected versions. And as you can see, instead of entering a death spiral of negative 0.1% growth, it was actually a not-so-fatal spiral of 2.2% positive growth, which is not exactly the same thing, right? So this took months and months to figure out. It happened after years. It happened after a lot of damage had occurred. And the question really is there something we, as computer scientists, could possibly have done to prevent this kind of catastrophe. So in computer science, we have a long tradition of working to help scientists, right? But you think of things like these supercomputing centers, even the very first programming languages like Fortran were really devoted to science, right? But they were devoted to the hard sciences. And social science is a bit different. It's social science, there's no beakers and sort of containers of chemicals. It's different tools altogether, right? So social scientists notably use spreadsheets and surveys as their primary instruments, right? So they're not mixing chemicals, they're typing data into spreadsheets and handing out surveys, all right? Now it turns out, of course, that social scientists are not the only people who use these tools, right? There's not 500 million social scientists. There are 500 million users of Excel, and that includes, of course, companies, education, government, and other sciences, right? Even the hard scientists are using these spreadsheets for their analysis. And surveys are also widely deployed, more than any conventional programming language. Right? So what I'm going to do in the rest of this talk is focus on these two instruments that are super widely used by social scientists to see if there's something we could do with programming language techniques that could actually help science. Right? So I'm going to talk about these two systems we've built. One of them is called CheckCell. And CheckCell is about finding problems with spreadsheets. And the other is called SurveyMan. And these both just got presented a month ago, I guess. So it's hot off the press. All right? So I'm going to start with CheckCell. So you look at a spreadsheet like this, and you think, well, OK, what are the problems? What's possibly wrong with the spreadsheet? So the core problem is that people make mistakes. Right? People make mistakes all the time. This is a representative Harvard economist here making mistakes. So what kind of mistakes do people make? Well, they can make the mistakes that we're all familiar with as programming languages people, right? They can have the program is wrong, right? The formulas themselves are wrong. But the input can also be wrong, right? And so if your program is right and your input is wrong, then your results are no good. If your program is wrong and your input is right, your results are no good, right? And, of course, both could be wrong. And in fact, in the Reinhart and Rogoff spreadsheet, that was the case. They had wrong data and they had wrong program. So just to focus a little bit on the data and why data is going to be a problem, right? So that spreadsheet has formulas and it has data. Those numbers were entered in manually. It turns out that people are really bad at this, or really good, depending on your point of view. Only 1.23% of characters are typically mistyped. These numbers, by the way, like the number of significant digits here, that's for real. These are the result of lots and lots of studies. Obviously, there's variance. In spreadsheets, this translates to about 5% of the cells being mistyped. So this is a result from a number of years ago, and this is a result that we actually just reproduced ourselves on a large scale. So it seems to stand the test of time. So what this means, right, is that if you have any reasonable size spreadsheet, right, if you have 100 cells in a spreadsheet, 5 of them are going to be wrong, right? That's the expectation. And if you have, obviously, that's just the data, right? There are other sources of errors. There are things like when you get data that's been generated electronically, right, that you collect from a sensor, the sensor could be biased. It could be broken. There could be a data transmission error. There's all kinds of problems, right? So here we're back to the spreadsheet. Spreadsheet has data. It has formulas. This spreadsheet, there's no way Reinhart and Rogoff, to be honest, I mean, there's some glaring errors, but I don't feel a huge amount of blame towards them because the spreadsheet is huge. It's staggeringly huge. It's about 20 sheets. It's 100,000 cells. It has many, many formulas. Consider the task yourself of having to manually audit 100,000 cells, right? It would be daunting. So it's not only daunting for a human being, it's daunting for a computer, right? If you have this spreadsheet, what you would like to have happen would be that it would do the moral equivalent of Microsoft Word, right? You type in a number, the number's wrong, a little squiggle comes up, or maybe Clippy comes back, right, and says, hey, there appears to be a problem, right? That would be nice, but it doesn't exist, right? And why doesn't it exist? So it doesn't exist for a variety of reasons. And some of these are actually kind of familiar themes in programming languages as well, right? So there's no spec. right? Reinhart and Rogoff, and in fact, no spreadsheet user really sits down and says, here's my specification of what a correct spreadsheet should be, or here's what a correct value for this should be, right? Those things are not present. They just don't exist. So this further means that since we know nothing about the inputs, we can't assume things like a distribution, right? So one of the things that you typically do to find errors is you say, oh, let's look at the, let's see if there's weird numbers, for example. But if you can't assume any distribution, then you can't actually do outlier analysis, right? An outlier is always with respect to some distribution. Furthermore, it's not just numbers, right? People have strings. What would it mean for, there's no sort of like Gaussian for strings, right? So we're kind of at sea. So what CheckCell does is it does something different. It leverages the fact that in a spreadsheet, we have two things. We have data and we have formulas. And so what we're going to do is we're going to actually analyze the interaction of the data with the formulas themselves and use that to guide our error detection, right? What it's going to do specifically is going to identify cells in the spreadsheet that have an unusually high impact on outputs, all right? That is to say that I've got some data, and this data turns out drastically affects the results downstream. That's the kind of thing that CheckCell is going to identify, right? And the reason that we focus on unusually high impact on outputs is that these things are really, really good to look at for two reasons. First, the data, if it has a huge impact, it means it's important. You probably want to make sure that that data is correct. If it's super important and it's wrong, then you have a problem, right? So this is where you want to focus your attention. And conversely, the stuff that has no impact on the final result, you don't care. So this could dramatically, in principle, whittle down the amount of time that you spend auditing a spreadsheet, and it focuses your attention on the stuff that matters. All right? So I'm going to walk you through an example of using CheckCell. This is an actual grade spreadsheet that mysteriously and in violation of FERPA is online. So we obtained it by spidering for spreadsheets. I encourage you all to do the same. You get quite interesting spreadsheets. So this is a whittled down version. And if you look at the grades right here, here's a bunch of different grades. There's homework, there's quiz, there's exams. And here it says the final grade is 84.275. And in our scenario, this is a graduate class. So you would fail the class. Okay? All right. So this has this spreadsheet here has the CheckCell plugin. This is the little window you get with CheckCell. And you click on this little button. It says Analyze. It spends a very little amount of time. It's pretty fast, looking for errors. And it says, hey, 78. That cell looks strange. So it marks it in red. Right? And then you can go and look at the thing and fix it. You say, oh, it wasn't a 78. It turns out it was an 87. So you enter the corrected value. It fixes it. And it shows one more. It says, hey, here's another thing. This is the next most significant thing. And then you can say, no, this one is fine. You mark it as OK. And then it's done. All right? So that's what CheckCell does. So how does it work? All right? The way it works, first, it does a traditional kind of program analysis. It does something called, it generates a dependence graph. So it goes through the spreadsheet, and it identifies all of the input cells, which are shown in green, and all of the outputs, which are these formulas. So these things are formulas that take these inputs. And you can see there's intermediate ranges, and all the cells feed into these ranges. Turns out this was a ridiculously difficult engineering task because Excel doesn't export this directly, and it has crazy, crazy, crazy things you can do in Excel that I had no idea about, so it was definitely painful. But once we extracted the dependence graph, this meant, all right, now we know that there's all these inputs, and we know there are all these outputs, but how do we find the ones that matter? Right? So let's go back to the spreadsheet. If you look at these numbers, like if you look at the 78, which CheckCell identified as being a problem, this is not an outlier in the data. Right? There's actually a lower grade, right, in the homework. It's a 77. So you would not just say, oh, 78 is bad. Right? The reason that we're going to identify 78 as bad is because of its impact. And so here's how we can assess its impact. So these are the inputs. This is the input range that is consumed by these. This is a weighting, and then it goes to this formula that gets to here. So we adapt a technique which was many, many years ago considered to be ridiculous and impossible, and no one would ever do it, because it was incredibly time-consuming in the computers of 1979. It turns out in the computers of 2014, this is really fast. So this is a technique called the Bootstrap. The Bootstrap is a non-parametric technique for doing statistics. So what non-parametric means is we don't assume any distribution. So there's no like Gaussian assumption, there's no uniform assumption, et cetera, et cetera. There's no assumption made whatsoever. So let me walk you through what the Bootstrap does, and then I'll show you what we do in CheckCell. Right? So the Bootstrap is a resampling technique. So you have some function, and the function has a bunch of inputs. The question is, well, you get all these inputs. These are the inputs, and you got them once. But what you want is you want sort of what is the underlying distribution? Like, I would like to know something about the distribution that these came from, but I have no information. So how can I extract information when I don't have any distribution at all? And so what the Bootstrap does, it says, look, your sample right here can be used to generate a whole distribution. And what we're going to do is we're going to randomly draw with replacement from this thing and make new samples. So for example, 78, when we randomly draw, it could get picked once, it could get picked twice. Very, very, very unlikely it would get picked 100 times. It could clearly get picked no times. Right? So we do this over and over again. Right? And you can see that in the previous slide, so we had a fail. With this resample, it's going to pass. Then we get another pass. We get a fail, and so on. So we can do this many, many times very, very, very quickly. And this gives us an empirical distribution that gives you a sense like, well, what is the likelihood of a pass versus a fail over all of these inputs? Right? So you can get a graph that looks like this. So it seems like pass is somewhat more likely than fail. All right? Fine. So what does CheckCell do? So CheckCell goes and isolates each input individually, every cell. In this case, what we've done is we've excluded all of the outputs that depend on the cell that contains 78. Right? And as you can see, there's a lot more passing that happens. Right? So this is the result that you get when you exclude 78. So what that tells you is 78 is weird. It has a significant impact. If it's gone, it changes the results. Right? So if you look at it statistically, you can see, I'm just going to show it graphically, you can do a statistical test. You say, how likely is it that I would have observed this just by random chance? And the default is that we say, well, we want that to be below 5%, which is pretty standard. If that happens, CheckCell will say, hey, this is high impact, and it'll report it. Right? So I'm eliding over details that CheckCell also handles. It ranks things, right? So it doesn't just present all of the things. It picks the most impactful and less and less and less and so on. It handles string outputs and so on. Right? So it works pretty well. I'm going to explain how we evaluated it. So I mentioned that we used a bunch of spidered spreadsheets. So we had to use, the one limitation of this is that we had to use spreadsheets that had formulas, because CheckCell relies on formulas. No formulas, no CheckCell. Right? So clearly, we could just run CheckCell on all these spreadsheets. Right? That's easy. We definitely can do it. We did do it. Unfortunately, it reports errors, and we have no way of knowing if they're errors or not. Right? We didn't go and email people at the various places we stole their, scraped their spreadsheets from, say, hey, cell number A5 seems weird. What do you think? Right? That we did not do that. All right? So what we did instead is we generated errors. All right? So this is a tried and true technique. It sounds super sketchy, but bear with me. All right? What we did is we took these spreadsheets and we added errors to them. Now, the question you should be asking yourself whenever you see anything like this is, yeah, but I mean, the errors you added, obviously, they're just sort of errors. Are they really representative of the kind of errors that people make? So the answer is yes. But before explaining why, I need to make sure all of you are aware of this thing called Mechanical Turk. So how many of you have heard of Mechanical Turk already? All right, wow, great number. OK, so then I can go relatively quickly. So Mechanical Turk is this Amazon service. It lets you post jobs. You can go, I don't recommend you do this, but you can go make money, not much, working on these tasks that are called HITs, human intelligence tasks. And you can hire people. So you can, for example, post something like this. This is a real screen grab from an MTurk task. It's by some company called Classify Ad Images. And it says, please enter the name of the product being advertised. and manifestly it is hipsters. So you enter the name of the product. There's all these buttons and so on. All right, so you can do this. You can have arbitrary images, arbitrary questions. And you pay, so here it says 10 minutes. You can see the pay is 6 cents. So it's a pretty, you'd be surprised how many people do these things. They do a ton of them at once. And some of them, I guess, are doing it instead of playing Minesweeper or Dots. But in any event, it's an available source of human effort. So what we did is we took all the spreadsheets, and we generated images, and we posted them as human tasks. So they're just images, and we said, just transcribe this data. That's all we asked them to do. So we got almost 170,000 retyped strings. From those retyped strings, we built a generative model that actually lets you say, well, if I have this character, what character could it have been typed as? What character would be next? So it handles typos and transpositions. Right? So then we applied that to all the spreadsheets, and that's our source of errors. Right? And then we ran CheckCell on it to see how it did. So the problem is I can show you a result, but it would be nice for there to be a baseline. There is, unfortunately, no baseline. Right? Nobody has done this before. So we had to use our own, like invent our own baseline, which is this Gaussian. So pretend we just do outlier analysis on the data. So we're only going to run this against numeric inputs because it's meaningless for Gaussians to talk about string inputs. But whenever we see an input that is out at the tails of this distribution, we'll report it as an outlier. All right? So what we're going to do is we're going to take all the inputs, we're going to run them through a Gaussian, we're going to find the outliers, and then we're going to compare those to what CheckCell finds. Now, it's important to remember, CheckCell is doing something very different. Right? It's looking at the input data and the outputs, and then it's reporting data with unusual impacts. That is to say, it's connecting up the outputs and the inputs. Yes?
I didn't understand the task that you gave to the people working.
To the workers. Yeah, so the question was, what was the task that I gave the workers exactly? The task was as follows. There's an image. It has a picture, like we literally generated a PNG of a bunch of cells. All right? This prevented them from copying and pasting the data. Then they had to type in the values corresponding to each cell. And we gave them something like 8 cells to enter for each task.
Oh, I see.
OK?
So you basically simulated errors in input entry.
Yeah, exactly. Just transcription, which in fact is pretty close to what happened with Reinhart and Rogoff. So what Reinhart and Rogoff did, well, OK, not them. They're graduate students. What those poor bastards had to do was to pour over tons and tons of data in printed form about, from reports of economic activity, and then they went and entered that data into a spreadsheet. Okay. All right, so I'm going to go through the charts really quickly because this is boring. It's awesome, right? OK, whatever. So it corrects more often. It's correct more often, so this just says as the output increases, the mean precision here, this is going up. The dotted line is us, and the bottom line is Gaussian. And this is sort of intuitive. As everything gets full and full with more and more errors in the output space, this does worse and worse. It also has higher recall, so it finds more errors. And then finally, this is really about the effort. So the amount of, the way we quantify effort is how many cells would a user who was actually using CheckCell have to actually examine. Right? So if we use the Gaussian tool, then there's less effort. So you might think, wait. The Gaussian tool is less effort. Yes, because it reports fewer errors. Right? So it finds fewer errors, but that translates to less cells being pointed out. However, the amount of effort that's involved, this means that they have to visit around 0.03 of the spreadsheet to find all the errors. Right? That's a lot better than visiting all of it. And finally, it's pretty fast. This is on this suite of benchmarks, spreadsheets. And the worst of them took a little over a minute. And on average, I think it was about 15 seconds. So it's pretty quick. So let's go back to Reinhart and Rogoff. So we actually, because conveniently the economists who had worked on this were at UMass, I met one of them at a coffee shop, brought him over to my lab. They said, hey, we're going to run this on Reinhart and Rogoff for the first time. And we'd like you to be there and tell us what you think of the errors it finds. So the very first one, this is the first cell that it picked up, it's hard to read, but it says 10.2. And my colleague, Michael Ash, goes, oh yeah, Norway. And we're like, what? Norway. And so it turns out they have this big document where they analyze all of the errors that they found. And there's a lot. And this one is really, it has a huge impact on the results. So this is a quote from their paper. This one extraordinary growth experience, Norway, contributes 5.3% of the weight, even though it constitutes only 0.2% of the country years in the category. Let me explain the methodological error here. What they did is they binned all of the GDP debt ratio things in 30s, 0 to 30%, 30 to 60%, 60 to 90%, more than 90%. And it turns out that Norway spent 1 year in one of those categories. And it was treated as if it had equally, really, with countries that had spent maybe 150 years in that category, because they didn't actually weigh it for the number of years, or divide it out, I would say, by the number of years it spent in that category, which is crazy, right? I mean, that's just not smart. I know this is being recorded, right? It's a crazy methodological error. But what it did is it accentuated the impact of this data, and therefore, it's not that the data itself was wrong, but it exposed a methodological error. So it turns out that CheckCell in total reports 10 errors. And they're all errors in the spreadsheet. They're either typographical errors, so it actually found data entry errors, or it found methodological errors. Right? So you can download this yourself. Unfortunately, the latest version works for Excel 2010 and 2013. We also have a prototype that works for Google Spreadsheets. Google Spreadsheets are a bit of a pain because you can't just do thousands of bootstraps over Google Spreadsheets, because every single one involves a round trip to the server. So we actually had a Google Summer of Code student who implemented an entire Excel recalculation engine to handle it client side. So it's not bad. It's not as fast as Excel, but it's pretty good. All right, so that's it for CheckCell. So now what I'm going to talk about is SurveyMan. You have a question?
So go back one slide. So
sure.
The Herndon et al. Paper is not you.
It is not me. No, I want to make that crystal clear. Yeah. I mean, I certainly want to allay any confusion.
Of the errors that they found, did you find all of them or more of them?
OK, so we found a lot of errors that they found, but we did not find all of the errors they found. So one of the errors that they found, it would be nice to figure out actually how one would attack this error. It's a very strange error. So it turns out that whoever actually constructed the spreadsheet, and I have a copy of the spreadsheet. I can't distribute it, but I can show it to you if you're interested after the talk. It turns out that, so they have all these countries, and all the countries, like it's Australia, Belgium, blah, 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 all in alphabetical order. Those are on the summary sheet. So you can actually see some of the summary stuff right here. All right? And you can see that for whatever reason, they're in inverted alphabetical order. Right? And they have this summary statistics at the bottom. And their summary statistics, which they copied and pasted over and over again, excluded 5 of the countries. All right? So it excluded Australia, Austria, Belgium, Canada, and Denmark, which, as you probably are aware, are really, really thriving economies. And just restoring that fixes a number of errors in the spreadsheet, but not by any stretch all of them. But finding that kind of thing is really tricky, and I don't see an easy way of finding it. It's a kind of structural problem. Yes?
As a related question, after fixing those 10 errors the CheckCell found, how close did the results of the spreadsheet get to the real results of the 2.5?
That's a good question. So I actually don't have the answer to that. So I know that we went through them all. It was my graduate student who did it. But I don't know that he evaluated that value. So that's an excellent question. I will ask him immediately. Yes?
Some of the errors you mentioned that affect Excel and data input, and some errors in formula, they also can happen if you're programming a regular programming language. I don't know if a tool like that exists, but have you thought about trying to do the same thing, but for regular programming languages?
Yeah, so the question is really, can we apply some of these techniques to regular programming languages, like not Excel? Some of the less widely used languages, like C or Java. So we have thought about it. It's complicated by the fact that the inputs are much more constrained when you're living in Excel. right? Like there's data, and you can know something about the data. But a lot of programs take file inputs, right? And very, very structured, even grammatical, things like, think of HTML, right? Where there's a grammar. Doing a Bootstrap on something like that does not seem obvious. Right? It's not clear how to do it. On the other hand, there are other data-intensive programming languages, notably databases. Right? So I actually am working currently with one of my colleagues who is a database person at UMass on applying this technique. So we refer to this as data debugging, applying this technique to databases. So thanks. All right. So I'm going to move on to, one more question. Yes?
So this is a general question. But do you think one of the reasons we fail to catch these errors is because we have these large amount of data items, like 100,000 items, and we put them into 1 or 2 parameters or outputs finally. So by the time we reach there, we have lost track of what was really playing what sort of a role. So if you go back to the spreadsheet example of grading that you gave, then one thing I could possibly do is club all the homeworks together, club the quizzes together, club the findings together, and see that the person was passing in the first 2 categories, but he failed in the third one. So I can just go and debug the third part and not bother about the first 2 sections at all, thereby reducing the space that I'm considering. Is that something that makes sense? But typically you won't have information about the databases.
Right. So, to sort of rephrase your question, there are other ways of doing data analysis, right? Maybe not automatically, but manually. And should people be doing those sorts of things? So there are nominally best practices for doing data analysis, right? And this is even true in spreadsheets. So you could do cross-validation. You could do things where you have, sums in some categories, sums in other categories, and check things. It's sort of like double entry accounting. Right? There's certainly plenty of techniques you could imagine adopting. People just don't, right? People are it's like programmers should all have unit tests and integration tests and system tests and do code coverage. And, they should also, just be good people, right? So, it would be nice, but it's just not necessarily the case. Yeah?
Is there a risk of introducing a strange sort of bias where if someone makes a mistake and you have some what should be ordinary looking data that somehow has a mistake that it stands out, you catch that error and you correct it.
Mm-hmm.
But if someone has perhaps an unordinary looking entry in some cell that they've made a mistake because they're, who knows, maybe they've just typed in the same thing all day and they type in the ordinary thing, then you're less likely to catch it because it looks like everything else. So it's like if there's like a sort of a homogenization bias.
Right. So your point basically is, just to repeat for the video, basically what CheckCell is doing is it's finding things that have an extraordinarily unusual impact on the final results. And in principle, if people were using CheckCell, then they'd be sort of creating a one-sided bias against things that have a major impact on the results, whereas things that were typed sort of the thing that was true would have had a significant impact, and they typed something else, CheckCell is clearly not going to find that. Yes, you're right. There's no way, if somebody doesn't type it in, it's difficult to know like what the correct thing is. Really, in a sense, what we're doing here is a proxy for trying to understand correctness through this lens of impact. But outside of the lens of impact, I don't know how to do it, to be honest. Right? And more information would certainly be helpful. But the problem is that the kind of validity checks that people might do would be like grades are between 0 and 100. And that really is not going to help very much, unless you do something really stupid. OK. All right. Thanks for all the questions. All right. So let's talk surveys a little bit. All right. So spreadsheets are everywhere, but surveys are too. And they're used in all sorts of different domains. They're used in industry, psychometrics, politics, government, etc. How many of you all have taken a survey in the last few months? OK, so basically everybody. All right. So surveys are happening all the time. They're used to inform lots of decisions, right? When they go and they issue a survey, the point of the survey is to say, hey, there's something I want to know about, and I'm going to act on that. Right? So how do people actually today build surveys and deploy them? So what they do is they create their survey, often in some web-based tool. They deploy it, usually not so much like this anymore, although this is still done. And then they take they've got all of the survey results, and then they run it through Excel, basically. all right? Sometimes are, all right? So this is the typical workflow. So we view this, when you're a programming languages person, you look at this and you think, of course everything's a program, right? So this is sort of like writing your program, you run it, and then you analyze the results, and you're done, okay? So is there anything missing with this, this workflow? Debugging, yeah, I hope that most of you were not like, no, that's what I do. I immediately submit my programs, like it compiled, done, all right? So the problem is, this is not a good strategy, right? So you might want to test things, especially if you count on the results being correct. So, surveys are not sort of obviously a programming language. They do actually have some similarities, and I'll explain briefly. Like, if you think about it, you have a sequence of things that you're supposed to do. You respond to them. There's some logic. There's the moral equivalent of if statements, right? If your answer to this question is this, go to question whatever. So typically, they don't have cycles. So it's not a Turing-complete programming language, but it is a programming language. But the bugs that you get are very different. So here are a bunch of different kind of bugs, and I'll explain them in a minute. And if you don't account for all of these bugs, soon the Dos Equis guy is covered in bugs, which is just disgusting. But really, seriously, it means that the results are invalid, right? Whatever conclusions you draw are probably wrong. And so SurveyMan is designed to attack this problem of surveys that may or may not be correct, and we want a way of debugging these surveys and making sure that the surveys are in fact correct so that the analysis we get at the end is true. Right, so the workflow with SurveyMan, it's similar. What we do, and basically we have the SurveyMan programming language, which is actually a secret programming language. So we embed it in a spreadsheet. You can just write it in a spreadsheet form and then run it through SurveyMan. And then, for people who do the surveys, they're like, oh, just enter something in a spreadsheet. They don't realize they're programming, right? We then can either post it onto the web, so SurveyMan is a web server, and it can host the survey itself, or you can post it to Mechanical Turk. And then, crucially, it adds this debugging loop, right? So it goes and it submits stuff to Mechanical Turk, and then it obtains information and provides it back to the user as feedback. And the user can then refine the survey, fix it, redeploy, et cetera, until they've weeded out all the bugs. And then finally, they get results that are actually valid. All right? So I'm going to give you a brief overview of the language. There's a lot of detail that I'm not going to talk about, but briefly, it's a tabular language. You have these columns like question and options. These are the only ones that are required. If you want to order the questions, then you put this block column in. Otherwise, the questions could appear in any order. All right? This here says that this belongs to block 1. I'll explain some of this notation in a minute. And this says that if you answer this question yes, then you would go to some next question following this question. And you can give specific numbers a la go-to statements. All right? OK, so let me talk about the kind of bugs that you can have in a survey. Right, so there are bugs that you can have both in the survey and in the respondents, which is a little weird. So I'm going to talk about the survey first. All right, so the first kind of bug is something called question order bias. So when you administer a survey, it turns out that the order in which you ask questions can actually influence the way people respond, which is not good. Right? And if that happens, it means that you can draw conclusions which are actually not due to the sort of ground truth of reality of how people respond, but an artifact of which questions you asked when. So here's a question. These are all drawn from real surveys, by the way. Do you favor or oppose allowing gays and lesbians to marry? 33% in favor. But civil union question, 45% in favor. Right? So you're like, oh, OK, 45%. However, when these questions were offered in the reverse order, then the number of people in favor dropped to 37%. By the way, this is a huge sample, right? So this is thousands of people being surveyed. So it's not like, this is very much statistically significant, right? So what's happened, you might be able to interpret it saying, hey, if you put forward for some people this marriage question, people were less in favor of marriage, but then they saw this as sort of like, OK, that's not so bad. But when you presented this first, then they immediately sort of responded as if they'd seen the marriage question. All right? So that's order bias. Another problem is wording bias. So this is a survey question from a while back. as you can tell. And the survey question was done by Pew, which does all kinds of political surveys. And so they asked two forms of this question. Do you favor or oppose taking military action in Iraq to end Saddam Hussein's rule? 68% in favor, America. But when you ask what is nominally a semantically identical question, but as you'll see, slightly different in wording, right? Even if it meant that the US forces might suffer thousands of casualties, which is sort of implicit in a massive military operation in Central Asia, it dropped to 43%. Right? So this is a pretty significant bias. And you could argue, look, these two questions are really identical. But if you report one, you report the other, you draw completely different conclusions. So you would like to know if that kind of bug exists. All right. Finally, there's this problem, which is actually a really, really huge problem on the web. It's called breakoff or abandonment. So breakoff is where people are taking a survey and then they quit. Right? So this is bad because it can skew the survey results. Because there's a whole sample of people who might just say, I'm just not taking the survey anymore. And that may be the sample you really care about. Right? Or it could bias the sample. So here's a sort of canonical example of this sort of problem. This is when you have an offensive or problematic question. And I should add, this can even just be things that, in general, people feel are asking questions that are too private. So things like demographic questions often trigger abandonment. All right? So there was actually a survey that was done by Pew on political ideology. And you can totally see where somebody was thinking how this survey would go. They had like a little hidden hypothesis here. But this was a question on the survey. Have you ever been unfaithful to your spouse or partner? Right? Please type this in and sign your name. Right? So, you know, it's kind of unsurprising that people ran away. Right? Not many people continued through that question. In fact, a whole subset of the population dropped out. Now, why did they drop out? Right? Well, did they drop out because they saw this bad question? Did they drop out from some other issue in the survey? Did they drop out because they were bored? Right? How many of you have taken surveys and not completed them? Yeah. Right? So why? Right? It could be because it was too long, or it could be because there were problems. And if you have those problematic questions, you want to debug them because you want as many respondents as possible. All right? So again, this is if you have this overly long survey question or an overly long survey. This is a problem as well, right? So if you have a survey and people are dropping off because of a bad question, that's bad. But if you had a giant survey, that's also a problem. And you might think, well, how giant is giant? For some people, depending on the questions, it doesn't have to be very long. This one is one of my favorite surveys. This is a survey that is administered by the Department of Health and Human Services. It's called the National Health Interview Survey. So this is one of those things that they sample and send out to people like the census, but to far fewer people. It's 20 pages long. Honestly, it's amazing they get any results at all. Like, they should be, I mean, I don't know. I feel like you'd have to pay me a lot of money to fill out the survey. All right? But in any event, people abandon the survey, right? So that's a problem with the survey. All right, so these are all the stuff I talked about were problems in the survey itself, in the survey program, if you will. But there's also problems when you deploy a survey, especially when you deploy a survey online. But it's true really even in controlled contexts. So, you know, some people, when they're taking a survey, they will just answer randomly. All right? They'll just get tired. They'll become inattentive. They'll just like zone out, and they'll just start Christmas treeing the survey. All right? This happens. And it's very difficult to control for on the web, right? You just get these respondents. Worse, all borderline criminally worse, is that people have actually put together bots for answering surveys. So, you know, there's surveys, lots of surveys are posted on Mechanical Turk. You can make money answering surveys. Money plus internet equals scam, right? It's a well-known formula. So the problem basically is that people have created plugins for Firefox and for Chrome to help you enter surveys faster. Right? So it just randomly chooses buttons, and then you click submit. So hooray. Right? So the answer, of course, is that if this happens enough, your results are also invalid. Right? So now I'm going to talk about how we're going to debug these surveys. So this all starts from having a programming language representation of the survey. right? We need this sort of programming language itself so that we can do stuff with the language at runtime or statically, but mostly at runtime, to diagnose these problems. So for example, this order bias question. So I'm going to go through a motivating example. It's a little shorter. It says, how often do you vote? Always, sometimes, never. Do you oppose or favor taking military action in Iraq? Yes, no, maybe. Okay? I guess I should say oppose or favor. But anyway, you get the idea. All right? So there are these two questions. When SurveyMan runs, it deploys a little JavaScript payload to your browser. The JavaScript payload incorporates a little finite state machine. The finite state machine is differently randomized for every single user, right? And so what it does is if you have not specified ordering on questions, then it will go and generate different permutations for different people. Now, clearly, you could over-constrain your survey. You could say, this must appear first, then second, then third, then fourth. The more order you put in, the harder it is going to be to diagnose these problems. So SurveyMan's language is intended to sort of nudge people away from doing that, which is why you have to explicitly put in numbers if you want ordering. And you can say things like 1, 1, 1, 1. That means all of those questions those must appear before 2, but they can appear in any order. Right? So what happens when these get deployed is that, say, this dude, the cool dude in the sunglasses, gets a survey, and he starts answering his survey. He gets question A first. Right? And he answers something in question A. He says always. Then he gets question B, and he answers no. Right? This clueless dude over here gets a different survey. He gets question B first. Right? And so now he has his responses. He says no. He says sometimes. And you can see he said no, and he said no. Right? Both of these guys said no. But what we can do now, because we have this different ordering, is we can actually compare the results. Right? So here is a case where we can see significant effect due to question ordering. Right? So these are the responses, and you see a very different effect. Whereas here, in this case, we see no different impact. Right? And you can apply a standard statistical test to actually identify whether there is this bias. And so right now, SurveyMan has a kind of primitive, old school programming language style approach to this sort of problem. It actually reports things in a report, and it says, hey, there's order bias detected. It applied the chi-squared statistical test. The p-value is very low, meaning it's incredibly likely that this is an order bias. Yes?
Isn't there a problem in that, standard statistical test, you assume there's like a single hypothesis. And here now, if you've got like 100 questions in your survey, and you want to consider every kind of pairwise order bias, then now you've got like 10,000 hypotheses, and one of them is going to reach a very high statistical significance that there's order bias, even if there's no order bias.
Yeah, so the question basically is this traditional problem. If you apply too many hypothesis tests, then if you have a p-value of 0.05, that means that one out of every 20 results are going to come out as being false positives. And the more times you test a hypothesis, the risk increases and increases. So there are well-known techniques for coping with this family-wide error rate stuff, and so on. In this particular case, the number, essentially, we're not looking at, should I describe this? It's not really exactly multiple tests. What we're really doing is observing multiple distributions and doing testing on the distributions themselves. So it's not exactly a hypothesis. I've spoken to a stats colleague of mine who assures me that this is not an issue and that controlling for FWER is not relevant in this context. But, so I defer to the statistician on this. OK, so we apply similar tests to discover wording bias. The problem with wording bias is that we can't just generate arbitrary variants ourselves, right? You can't just like put into a sort of black box, here's this question about Iraq, right? And spin a grinder, and then it pops out and says, what about casualties, right? So what we do is we make it possible for people who are writing these surveys to encode what they think are similar wordings. You can imagine automating things from some pool. Here we say these things are all in the same block, and you can give them some identifier as long as it starts with a letter. If they have the same identifier, then it means that they're logically the same question. So you can have an arbitrary number of these variants. So you can see there's the favor or oppose, and then there's the favor or oppose, even if it meant casualties. All right, and there's the notation. All right? And likewise, things proceed in the same sort of way. Instead of getting randomized order, well, they still get randomized order, but instead of it just being randomized order, they get different variants of the question. So this guy might get variant A1, right? And he answers something. This guy gets A3, he answers something, and so on. So you build up a whole distribution. And you can apply the same sort of statistical reasoning to identify whether there's some sort of wording bias. All right? Yes?
So if I have some sort of bias and I'm creating the survey and I'm using your tool,
Yes.
I can use the insights to basically get whatever result I want to get.
Yes. So the question basically is, aren't you making it easy for bad people to do bad things? Or good people to do bad things? Or I don't know. You know, it's funny because I've gotten this question a few times now, and I clearly am not evil enough to have thought of this first. But it's true that you could imagine using this for ill, right? You could debug your survey by actually overfitting it to your desired hypothesis, right? Let me put it this way. Scientists already commit fraud, okay? Luckily, not that many, but they commit fraud. And the way that they commit fraud is they just report fraudulent results, right? So I ran a survey. Here, ready? Here's a result. I ran a survey of UCSD students, and they all think Soren Lerner is a jerk, right? It's like, boom, I just generated. Clearly false, right? Because he's a great guy, right? But you know, you don't need a special tool to gin up fake results. You just need, you know, key presses. So that said, you could imagine doing something for political will, for political ill, I mean. So there's this phenomenon that some of you have probably heard of called push polling. How many of you all know what push polling is? All right, small number. So push polling is a trick. It's a survey. It sounds like a survey. They call people up or they send people these surveys, but the surveys are not actually intended to elicit information. It's to transform their beliefs. So for example, would you be upset if you discovered that Obama ate live babies a long time ago? And you're like, yeah, that guy should stop eating babies. That's terrible, right? I'm not voting for him again. Right? So you know, this is a real problem. People definitely do it. You could imagine using SurveyMan in the sort of way to get people to do something, you know, to come up with some sort of like the support for the war, for example. You could ask people, if you ask people this second question, this is, in a way, you could view this as a kind of a push poll, right? You could say, hey, are you in favor of Iraq? Even if it means your kid and all of his friends are all potentially going to die. Right? That could actually transform somebody's opinion. So it's a great question. Yes?
But so how do you fix these bugs then?
Yeah, how do you fix the bugs? So there are two things that SurveyMan does. So first, it identifies that there's these biases. The second is it controls for them. Right? Because you're doing randomization, you can actually exclude the effect of the bugs. So it leaves you with two choices. One, you say, well, I ran this experiment, and here are the survey questions that I actually reported. That is, you actually say, here's the SurveyMan code, right? And then you have these experimental results which happen to cope for all of these issues. Or you say, there's something really wrong with the survey. This is getting very, very strange results, and I just eliminate it from the survey. So it's really up to you. Yeah?
But so in the end, let's take this example. What's the truth? You know, right? I mean, so there's a bias, but there's a bias in both directions, and it's capturing the fact that the way people feel about it is complex. And the way we like to use surveys is to pretend that the way people feel isn't complex. And then we can represent a number. On the other hand, that's nice because parsimony is something that's easy to deal with. Giving someone, here's 30 pages of code and all of the, you know, all the covariance matrices between how people, it's hard to make a lot of sense out of it. So
I agree. What's the answer? So the question is, when you get results that are the result of bias, right, what is the correct answer? What's the underlying truth? So you're absolutely right that surveys, the whole point of the social science endeavor is to uncover the truth. On the other hand, sometimes the truth is messy, right? Not just sometimes, to be honest, right? And the problem is, from my perspective, is exactly what you're describing. People have adopted this illusion because of the tools they've been using. Right? They deploy a survey, they get results, And they're like, and we're done, right? Problem solved. The problem is that they're not accounting for all of these biases. And what they should be reporting is much more detailed, much more nuanced information. But I think that you could argue, what's the truth? Is the truth that people prefer war with Iraq, or that they don't prefer war with Iraq? Well, the truth is actually conditioned on the question. It's conditioned on the way you ask the question. Yeah?
So people have a bias that we want simple models, we want simple answers, and the truth is complicated, but a compromise could be to report a slightly more information, which is you could, right now, generally the way people use survey information, we only look at the averages. If 70% of people said X, and instead of use 3 numbers, then you could say, here, this is the amount by which people's opinion, based on what you observe with their bias, from order bias or whatever. You could say basically you can sort of put a bound on how consistent they are. You could say, okay, we can get people to say anywhere between 50% and 90% by manipulating obvious biases. So
absolutely. So I think that using randomization actually gives you the opportunity to use confidence intervals in a much more meaningful way, right? So you can typically report confidence intervals anyway, but the confidence intervals are much richer if you actually have done some sort of randomized experimentation. So you could imagine saying, hey, it's 50%, but the confidence interval is like this. I do question the ability of ordinary people to actually grok these things, but it's certainly an option. All right, so I'm just going to move through the rest of the stuff that we deal with. The way that we handle breakoff versus abandonment is also based on statistical inference and randomization. And the way it works is pretty simple. We essentially try to see whether people leave a survey because of a particular position, right? Like there's some Gaussian around some position, or because of some particular question, right? So here's somebody who took question A and question C and question B and then left, right? So we tip, they say, well, this is position 3, and it was question B. And then we do the same thing for somebody else. They get the questions in a different order. They left at question A. Whoops. They left at question A, sorry. And then we get a 1 here, and then we put a 2 on position 3. And so what you get at the end of the day is you get a breakoff by position. This means that people are leaving because the survey is long, right? Or a breakoff by question. It looks like maybe question C is problematic. All right? And then we rank them. And we just say, oh, this is what seems to be happening. All right? And finally, let me talk about bad actors. Homer and Bender, they're a problem. So basically the way this works is a kind of entropy-based calculation. So we kind of, if you think about it, if we're randomizing the order, and we randomize the question answers themselves as well, to the extent possible, people who are behaving lazily, like they always hit A, well, A is moving. So really, it's no different than somebody hitting A, B, C, D randomly. Lazy and random look the same, right? And this is by virtue of the fact that we're randomizing everything, again, to the extent possible. Whereas people who are actually answering properly presumably are not behaving randomly. Because if you have a survey and the survey has all this structure, you don't expect the world to have no structure and people have no opinions, right? So this has the effect, by discounting all of the stuff that looks like random noise, that is to say that has a really, really high degree of entropy, we're able to weed out the random actors and get the good actors. All right? So I'm going to conclude this discussion of SurveyMan with a pretty funny case study. There are 3 that we did in the paper. So this is working with colleagues of mine in linguistics and labor studies. This prototypicality one is totally crazy and a lot of fun. So prototypicality is a notion held by linguists which kind of harks back to Plato and this idea of Platonic ideals, right? So here is a chair, but it's a pretty weird chair, right? Is this like your canonical view of a chair, right? There's no legs, right? Usually if you ask a kid to draw a chair, right, it's like a chair, a seat, a back, and 4 legs. So this is a chair, but it's not particularly chair-like, right? So there is a belief among some linguists that people have this kind of nuanced view of almost everything, that they actually have like an ideal for all sorts of stuff. So this is a prototype. It even extends to things that you and I would not think as having any nuance at all. So this is an actual question from linguists. Say, how representative of the category of odd numbers is this number? 787. Pretty odd? Super odd? Kind of odd? A little bit odd? Not odd at all? So the belief is that the way that you can elicit these things is by offering a scale. Just like one of those scales that you've seen before, you know, unlikely, like very unlikely, kind of unlikely, sort of okay, you know, very likely, ultra mega likely, right? So when you offer up surveys, people will actually take those choices in the middle, which seems very strange. Well, it turns out we went and did these surveys and took a bunch of different wording variants from surveys that had been offered on prototypicality to measure this, this effect. And by the way, 787, it's only partly odd, because it has an 8 in it, right? 8's not odd, right? If it's 777, then sure, that's an odd number, right? So you do elicit this sort of weird behavior, but it turns out that there actually is some kind of wording bias at play. So it's not that people have some deeply held notion of, gosh, if there's even numbers in the odd number, maybe it's not so even. So here, these are actually, these are basically meant to show that for this particular question, people thought 463 was mega odd, and people did not think it was that odd here. And the wording is subtly different. It says, how good an example of an odd number is 463? And then, how well does the number 463 represent the category of odd numbers? You know, what did the survey designer mean when they said example, right? As an example you'd give to a kid, would you say, here's an odd number, 2468, 2463? No, because you're a jerk. Don't do that, right? It's a terrible example, right? Use a really odd looking number. So it appears this effect is really nothing more than the effect of wording bias. All right, so to conclude with SurveyMan, we now have this system. We've been deploying it. We've been working with social scientists where you write your survey, you can debug, deploy the thing, and you get accurate results. And finally, I just want to sort of turn this into a call to arms, if you will. You know, we've been working in programming languages for a long time. It's one of the oldest areas of computer science. But I think it's been a bit inward looking, right? We're really focused on programming language sort of efficiency or programming language correctness or tools for software developers. But there's a lot of tools that we've built up in our toolbox, right? So there's these old tools like static and dynamic analysis. And if you couple them with some new tools like statistical analysis, it turns out you can actually build these things that can provide value far outside of the reach of like software developers, right? Address completely different areas, in particular social science. So I just wanted to conclude by talking about, so a little shout out, these are my graduate students, Dan, Demeter, and Emma, and these are my collaborators in the social sciences. So everybody should get out there and debug science and stop the fireworks in Europe from happening again. All right, thank you.
All right, so we're a little bit over time, but do you have time for one more question if anybody?
Sorry, I was curious about the use of Mechanical Turk as a deployment platform. So Mechanical Turk tends to have a very biased population, usually poor countries, low-income people. So doesn't that skew the results as part of the debugging process if you say you want to deploy to the US?
OK, so the question is really about like Mechanical Turk biasing results. So Mechanical Turk actually kind of has a bimodal population. It has lots of Americans, and it has lots of people from the Indian subcontinent. It's biased especially towards English speakers. That's an issue for sure. The fact is that it's just a lot better than what people used to use in the social sciences. So in social sciences, the standard operating procedure was to take your undergraduate social science class. And those would be the people you would do your experiments on. Right? It's kind of hard to pick a more biased sample than, hey, let me take 20 kids from my class and do a study. But that was pretty much the state of the art. So Mechanical Turk is clearly better than that. It's definitely not perfect. One of the ways that we address this for the linguistics questions is that we asked people in the survey whether they were native English speakers or not, and then we paid them no matter what. So they took the survey, we kept the results, but when we separated out the results. So you have to be very, very careful in this population to not say, like, boy, if you answered this question this way, then you won't get paid, right? Or you won't get to do any more surveys because there are out-of-band channels for discussion. There's discussion groups, there's plugins, there's all kinds of stuff from Mechanical Turk where they'll be like, oh my God, go to this hit, it's fantastic, there's this survey, but make sure to answer question 1 this way. Right? So you have to be very, very careful about these things. So, care must be taken, but the reach with Mechanical Turk and the speed with which you can test things is phenomenal. And so it is really, really widely used these days in social science circles.
All right, great. Let's thank our speaker again.
Right. Thank you.